So can you see the screen now?
Yes, sir.
Hello. Okay, great. So let's start this classical mechanics course today. So today we will start with this Newtonian mechanics, which you are all familiar that, if a system of particle or a single particle, which follow the Newton's equation of motion, then we call this as a Newtonian mechanics, right? So this system can be a single particle, or it can be a system of large number of particles also. Now, if you know that for any system, like even if it's a single particle, so if I want to describe the system, basically you need to define some degrees of freedom of the system, right? So you can see like how, let's just actually start to understand what is mean by these degrees of freedom of the system. So you can say like if I have a one particle, say like this particle here, okay. Now for this particle, if I want to describe this particle, we basically need three coordinates, right? We need three coordinates. Say this X, Y, and Z, right? So basically for representing system or to describe the system of a particle, we need this coordinate system. Now, if you instead of this one particle, if the system has two particles, so then you need basically another 3 degrees of freedom, plus 3, right? So basically you need at least 3 positions to describe each of the particles. So if you have 2 particles, you basically need 6 degrees of freedom. So in the similar way, if you keep on increasing the number of particles, this number of degrees of freedom also increases. See, if I have n number of particles, then basically I need this 3n number of degrees of freedom, right? So for a one particle, you need 3 degrees of freedom. Say if I say these coordinates are like x, y, z. For 2 particles, you need 3 plus 3. And if you just keep on increasing number of particles, right? So what will happen? You basically need to increase the number of degrees of freedom to describe this system. Now, so for doing this, when we say that, for 2 particles, we basically need 3 plus 3 is equal to 6 degrees of freedom. Now, if you say that n number of particles, then we want to say that we need at least 3 number of degrees of freedom. Now, the question is that, describing these things, what we are saying that there is no constraint, like if you have 2 particles, so there is no constraint in between them. So basically, like, for this system, like, this is the independent particle, okay, and this is also independent particle. So you basically need 3 independent parameters to describe this system and 3 for this system. So as a result of that, you get 3 plus 3, like degrees of freedom. Similarly, for n number of particles, if there is no constraint between the particles, then you basically need this 3n number of degrees of freedom. Okay, so now let's try to understand what is meant by the constraint that we are talking here. So basically the constraint, you can understand like, you can say like you have a table, right? So like you have a table like this way, and so say there is a particle, right? So this is a table, basically this is a 2D plane, say like in the X and Y. Now, if this particle is actually moving in this table, which is a 2D plane, so basically the thing is that you are basically constrain this particle to be moved in this 2D plane, right? You are constraining them to move in this 2D plane. So what will happen? So basically you get 2 degrees of freedom for this system. Right. So what we are saying that, we are basically constraining the motion of this particle in this 2D plane. Okay, so this is our simplest idea for understanding the constraint. Now the thing is that, so for describing this degrees of freedom, this constraint actually play a very crucial role. Like if I have a system of different number of particles, now if I want to know what will be the actual degrees of freedom of that system, so I need to know about this constraint also for that system. So now you can understand like, in a simple way. So, like as I told you, if you have this free particle, there is no interaction or something like that between these two particles, then you can just use this coordinates information to describe this degrees of freedom. But when they are constrained, so you need to be careful actually to define the total number of degrees of freedom. So now, if you can, as I told you, if you consider a single particle here, like one particle, so basically what we have, we basically say this is like the 3 degrees of freedom, right? Now you consider another one particle here, say another one particle is this one. Now if these two particles which are independent from each other, then we have basically 3 plus 3, like 6 degrees of freedom in this case. Okay, now just imagine, so this is like say these two particles are connected by some string. Okay, so my drawing is not that good. So say this is like particle 1 and this is say like particle 2 you have, and they are connected by this string. So you say this R of 1, 2 between them is actually is a constant. If I say this is a constant, right? So if there is no string between them, so what we have this 6 degrees of. But now if I put a constraint that in this these two atoms are actually atoms or particle, whatever you want to say, they are connected by this string, and the distance between these two atoms or the particle is constant. So basically what happened, you are putting one constraint on this system. So in that scenario, what will happen, you basically reducing the number of degrees of freedom to 5, right? So this is the simplest system you can imagine. Now if I consider another one particle, right? So like say here, this is the third particle. Okay, say this is the particle 3. Now, if what happened now, like if all of them are independent, then you have the 9 degrees of freedom, right? Now, what will happen if I connected these 2 and 3? Okay, so then what will happen in addition to this R1, 2, you have basically R of 2 of 3 is also constant, right? Right. So what will happen basically in this system, the number of degrees of freedom will be 9 minus 2 will be 7. Correct. Now, if I do further, like if I consider a triangle, in this triangle, so we have put in like 3 particles of 3 atoms at the 3 nodes of this triangle, right? And what will happen this triangle? So as a result of the distance between 1 and 2, 2 and 3, and 1 and 3 are also constant. So if I say this R of 1, 3 is also constant, right? Then in that case, what will happen? Basically, you get this 9 minus 3 is equal to 6 degrees of freedom. So this is a very important concept to understand, because the thing is that if I want to write this equation of motion, right, for this system, so later when you go to this Lagrangian equation of motion, you will see you need to, from the Lagrangian, you can easily derive the equation of motion of the system. Now the thing is that for doing that, we need to know actually what are the degrees of freedom of the system, because without knowing that one, we cannot write down the equation of the motion of the system. So this is basically the simplest concept you can consider like this one. So now what we see, let's try to generalize this idea of this constraint and try to finding out these degrees of freedom for that one. Now what you see that if we have these 3 particles that we have here, and in these 3 particles, if they are connected by kind of string, which is like or some rod, you say, such the distance between them, and you can get these degrees of freedom. Now, if I like this n number of particles instead of these 3 particles, if I have this say n, right, as I told you, n number of particles. So, and you imagine that all this n number of particles, if they are not connected, like each pair, they are not connected, like these things I'm talking about, this one, if they are not connected, so then in that case, you get basically 3 number of degrees of freedom, right? Now, the thing is that just imagine in that n number of particle, if each pair is connected, right? Like this here, this triangle, like now for n number of particle, if each of the pair is connected, then what will be the number of constraint in that scenario? The number of constraint will be n times n minus 1 divided by 2, right? So basically, you when you do not have any constraint like this, all these particles or this n number of particles or n atoms, they are not connected with each other, then you basically have 3n number of degrees of freedom, right? This 3n. But now because of this pair, they are connected by some kind of rod or something like that, which is constant. So what you will get? You get basically this 3n minus n into n minus 1 by 2 times of degrees of freedom. Okay, so this is now the degrees of freedom for that in the particle system, where this we are considering this each pair is connected by some kind of rod, right? And you can actually use this formula to describe whatever the things we have calculated here. Okay, now just take a case of this n is equal to 4 number of particles, right? So if I considering this 4 number of particles, so what you will get this the number of degrees of freedom. If you calculate, you will get this 6, right? If you put in this formula, you will get 6. Okay, now if you go further, if you take this n is equal to 5, I'm going to the increasing number of particles. So what you get basically 5 degrees of freedom. Okay, and if you just keep on increasing, and if you go to say this n is equal to 8. Okay, now if you do that one, what you will get? You get a negative number, right? So if you, what I'm saying, like if you keep on increasing this number of particles, okay, yeah. So if you keep on increasing the number of particles, what we found that they are after a certain value of this number of particles, this number of degrees of freedom become negative. But this number of degrees of freedom is what? Basically, you can say this coordinate system to represent some some particle or a system of particles, right? Now the thing is that cannot be negative, right? Because this is a physical system. Now the question is that then how can we physically describe this kind of system that where these degrees of freedom become negative, and is it really physically it is feasible or not? So now to understand that things, the thing is that how should we explain this? So any one of you can explain this part, like how this become negative and how we can physically explain this?
Sir, the total number of constants are not independent.
Okay, yeah, but then how it become negative? Like physically, how we can say that they become negative? They are independent. Okay.
If the degree of freedom is negative, none of them can actually move.
I didn't get it clearly. Can you say again?
So when degrees of freedom are negative, it's so constrained that it can't even move.
It means you require more.
It cannot move. Like the particles cannot.
No, even without moving, just imagine, like if the particle is somewhere, like let's say rigid body, right? It's a fixed somewhere, right? I'm talking about the number of degrees of freedom. You don't need to necessarily this. We need to go for the motion of the particle. Even if it's a stationary particle, you still need to define the position to describe the particle, right?
We have more constants than required.
Exactly. So that is actually the right answer here. So basically, the thing is that for every system, like if you have a 3 particle or if you have a n number of particles. Okay, so basically the thing is that you need actually a minimum number of degrees of freedom to basically describe the system or hold the objects. So as a result of that, the sum of the these degrees of freedom, they become redundant. Okay, so basically you don't need that number of degrees of freedom to describe the system. So they become redundant actually, right? So basically the thing is that you need that minimum number of particles to describe. If you go beyond that, you're not necessary because they are already taken care of, right? So you do not need to put that constant again, which you have already considered to describe the system. Basically, you get this redundant number of these degrees of freedom or this constraint actually. So the things what we see here that that for every system we need a certain number of degrees of freedom. You don't need beyond that one. So let's take to understand this. Let's take an example of a maybe say what example should we take? Okay, so okay, let's take a simple example of a rigid body. So it's easy to explain here. So you just imagine that if you have a rigid body. See, my drawing is a little bit bad. Sorry for that. Okay, so just say this is a rigid body. Okay, and say as we are describing here that we need to define the coordinate system to describe any system, right? So whenever you define some body like rigid body, we need to define some, say this is a fixed coordinate system. Okay, say like this is x, this is y, and say this is z. Okay, now so we are basically saying that this is a rigid body and this is the location of the center of mass, say, and say the distance between this center of mass from this rigid body, so the rigid frame is, say, this r. Okay, so this is the coordinates, see, like the position coordinates, right? Now if this body is actually is fixed, right, you need these three coordinates is enough to describe the system. Now if you just imagine, like if this body is actually is rotating with respect to some axis, say like if you draw a z axis somewhere here, then what will happen, say this body is also rotating around this z axis, right? So basically what we found in that scenario actually is that we basically have these three coordinates or degrees of freedom to represent the center of mass of that one, and three basically we need to just to describe the rotation of the system. So basically for a rigid body, this 6 should be enough. This number of these degrees of freedom is 6 actually, and with these 6 degrees of freedom we can describe this entire system. As I told you before also that if I want to describe this motion of the system, right, through this Lagrange's equation or something like else, that the one important thing that we need to know very accurately what is the degrees of freedom of that system, right? So what we understand from here till now, that if you have a system of certain number of particles, they have each particles you can describe by certain not the system you can describe by certain number of say coordinates, and if you basically subtract this constraint from that one, then what you will get, you basically get the degrees of freedom, right? So that is the things we understand here. Now the question here is that whatever we have discussed, that we need to subtract this basically the constraint which is inside the system to get the degrees of freedom. I mean, is it absolutely correct or not? So that's we need to understand. So it's not absolutely right that say that I just calculate this coordinates, then I just subtract this degrees of freedom. Sorry, not this constraint, and I get these degrees of freedom. So actually, you need to go from different case to case to understand these things. So you can consider this case like, and as I told you, if a particle is moving on a table, right? Like this example that we have here. So basically, we see that it has a 2 degrees of freedom, right? In this one. Now just imagine if this table, so that is there is a finite length of this table, length and width, right, of this table. Correct. So just say that this particle is moving between. So this is, say, this is the length, and the other side you have the width. So now this particle is moving in this table. Now but you are putting also this constraint into this system that it cannot go beyond the edge. So when it reaches to the edge, it has to be come back, right? So you are putting the constraint on the top of this, that we have a particle that is moving in the table, but in what we constraint we are putting here, that there is a maximum length of the table and the width of the table, and this particle cannot go beyond that. So it has to be within this limit, right? So you put this constraint of that one. Now the thing is that we need reduce this degrees, will it reduce this degrees of freedom that we have here? Actually, it's not, right? Because the thing is that in addition to this, the motion that is happening in the plane, you are putting this constant that this particle cannot go beyond this edge, right? So that is actually a kind of inequality. So we call this is not a constraint. We call this is a inequalities. Let me say this. This is we call the inequalities.
Hello, sir.
Yes.
Sir, I have a question regarding. Can you please again explain how you got how 6 degrees of freedom are required to represent the orientation of represent the coordinate for any rigid body to represent all points to
Yes.
define all points. How did you get that?
Okay, so let's go to, so you have a rigid body, so basically rigid body means all the particles, or you can say atoms, they are connected with each other, right? So there is a fixed distance between them, like between all the molecules of the particle, right? So now for that kind of system, what normally we do, we always try to find the center of mass of that system, right? Is it correct? So now if you know the center of mass, so basically we need to, if you know the center of mass of that system, so from that one you can easily know like what is the location of each of the particle, right? So the independent parameter is actually the center of mass coordinates. Okay, then if you know that one, now if this rigid body is moving, if I say with some axis, so basically then you need this angular rotation, right? So basically you need another 3 coordinates for that rotation. So that 3 plus 3 will give you these 6 coordinates. So with the 6 degrees of freedom, you can basically describe this rigid body system.
Yeah. Okay, sir.
Okay. So now the things that we are talking about that, so we basically say that, if you have a particle that is moving in a table, right? So it is moving in a table. So we have, sorry, go ahead.
Sir, actually, what I'm asking is, suppose there are, when you have taken two different particles, single particle, so each have 3 degrees of freedom, other has 3 degrees of freedom. So when we have joined one of them, then does we have taken the rotation also into account in calculating a 5 degree of freedom, or
Yes.
just we have taken individually?
No, that's true. That's true. So here, or if you have a just particle, if you are not considering any motion of this particle, say like, this atom or something which is at rest, just, system. Okay. In that case, you can consider, because the 3 is actually the position of individual particles. And, one rod you have connected between them. So at that distance become constant, right? So you can reduce by that one. But if you definitely introduce the rotation, you need to consider this velocity. So basically, that's the concept we are going to for this generalized coordinate system, and in the phase space we will describe that one. So basically, we are going to that point slowly.
So then, if we will take the rotation also, then the degree of freedom will further increase for the two particle system.
Yes, absolutely. You need to consider that because that will happen in the phase space, right? Then.
Okay, sir. Thank you, sir.
Okay, so now the problem that we are discussing now, that a particle which is on the table, actually it's moving in the 2D plane, right? Now the thing is that it's such a 2 degrees of freedom, because in the third one you have already fixed that is moving in the plane. Now the thing is that if you put this constraint that this particle can move in the table, but it cannot go beyond that edge, right? So basically it's some kind of constraint you are putting into that system, right? But we don't call this a constraint, we call this a kind of inequalities, or you can say the kind of boundary conditions you are putting into the system. Okay, so now the thing is that these inequalities actually will not reduce your degrees of freedom, though it's a kind of constraint you are putting into the system, but it will not reduce your degrees of freedom, right? So actually then actually here this there is a theorem which comes here, which tells that if you can reduce this degrees of freedom. Okay, so what I'm saying, like just like you ask this question that we have 2 particles, then we have 6 degrees of freedom, and we put a rod between them such that the distance, right, between them is constant. So basically what happened, we put this constraint, so it will help to reduce this degrees of freedom from 6 to 5, right? Now if we have a system where we can do that kind of calculation or that kind of discussion that we have here, then we can call this kind of constraint are called holonomic constraint. Sorry, holonomic. or you can say this is integrable. Okay, so what is holonomic concept? Because during the entire class, actually, we are going to use this term actually, holonomic and non-holonomic. So, what is the idea behind this? We need to understand whether this constraint will reduce the degrees of freedom or not. So, if this constraint can reduce the degrees of freedom of the system, then we call this is a holonomic system, and you can say you can write this equation in the integral form actually, right? And if you cannot reduce the degrees of freedom, just like we discussed this particle which is moving in the table, right? So we put some inequalities into that one, but it will not help you to reduce this degrees of freedom, though you have put some extra boundary condition or inequalities, right? Help you to reduce these degrees of freedom, then we call this as a non-holonomic. Okay, so these are actually two constraints which is very important. Like we are going to discuss this and use these terms in the entire classical mechanics class. Okay, so basically the thing is that if you can reduce this basically degrees of freedom by using this constraint, then you can say this is holonomic, or you can write this one in the integral form or like that one. Or otherwise, if you have some say inequalities, a kind of constraint, but it will not reduce the degrees of freedom, then we call this is a non-holonomic system.
Sir, what do you mean by can write it in integral form? I did not understand.
Yeah, so I'll show you. Like just like case of a simple harmonic oscillator, you will see that we can write down this in the integral form or something like that. But in other case, we cannot because of this constraint. We will come to do this all these details actually. Okay.
Yes, sir.
Okay. Okay, so maybe I open another whiteboard. Okay. Okay, so now it's actually today you just try to understand like the coordinate system, generalized coordinate system. Okay, and what are the conditions we need to describe is what are the minimum number of coordinates that we need to describe a system, because later you see that we need to, when you especially do this equation of motion, if you do not know like what is the degrees of freedom, you cannot write down the equation of motion, right? So because if you do every equation of motion, there will be some constant of motion, you need to calculate that one. So basically, whatever be the boundary condition that you need to know. So as a result of that, you cannot have, so you have like say two boundary conditions and you have three equations. Then you cannot solve it, right? So basically, you need to know what is what are the actually number of constraints required to describe that system. Okay, so that is one important things to discuss. Okay, now let's understand these things. Like till now we just discuss about that. If you have a particle or a system of particles, we basically need certain number of coordinates, say like x, y, z, say in the Cartesian system, right, to describe the position of that particle. Now just imagine, like if I have this like this pen, now if I say drop this pen from here, then what will happen? It will just go down in the gravitational force, right? Just if I leave this pen, it will go down in the gravitational force, right? So now let's try to. So this is a very important concept, but it's very simple but very important. Say you have this particle or this pen, you say. Okay, so what will you just release this pen? Now what will happen in the gravitational force? It will come down, right? Like this. Now, if I know the initial position, say this is some like x0 or y0, z0, you can consider all these things. Just simplicity, you just consider this is some position, initial position of that one. Now, the thing is that, can you predict this next, what will be the future dynamics of this system? So, what do you mean by dynamics? Like, at the beginning, say at the time t is equal to 0, okay, I know this is the position of this particle. I know that one, right? Now, can you tell me what will be the position of that particle at t is equal to say 15? right? So in this case, what happened? You are allowing this particle in the gravitational force. So I know it will just fall maybe a straight. I know what will be the location of the particle. Maybe easily I can calculate that one, right? But just consider another one case. Say this same particle you consider here. What you will do? You give some a small, horizontal force direction. You give some small horizontal force, it will not follow like the same path that used to have like this, right? So it may go like this, right? Now, if I consider the same particle, if I give little bit more, like compared to this one, then what will happen? It may go farther, and it can fall like here. Right. So now just see, I know the initial position of all these three. Say this x0, I know. Now, can you tell me, like, only with the information of its initial position, can you tell me the future of this particle, like where it will be at next time step with the information of the position? Because you need to know that for every particle we are, so here we are not giving any horizontal force, but for these two particles, this second and the third, I gave some horizontal force. So if I give some horizontal force or horizontal velocity, whatever you want to say, now can you tell what will be the future, like the position of that particle? So you cannot, right? Because the thing is that you just imagine, if you do not know the velocity of this particle, initial velocity of the particle, so whatever be the equation you use, like S is equal to Vt or whatever formula you use, so in all this formula, what you have, basically you need to know the velocity of the particle also to predict the future of that particle, right? So I started with the initial position, right? Now, if I give some kind of, say, horizontal force, this particle can go like in the elliptical path or can go in the parabolic path, right? It depends on the the force or the horizontal velocity that you are giving to the particle. Right. So basically the thing is that only knowing this position of the particle or the initial position of the particle, you cannot predict the future. Right. So what is the main point I'm trying to emphasize here is that in addition to this initial position of the particle, you also need to know the initial velocity of the particle also to predict the future of the system or future of the particle, right? So is it clear to you all?
Yes, sir.
Okay, so the thing is that, so basically the idea is very clear that without knowing the initial velocity, how can you, so all the formula that you guys know, like is equal to Vt or whatever, all these are associated with the initial velocity or something like that, right? Now the thing is that if you do not know the initial velocity of that particle, in the next time step, I mean initial time step, you know what is the position. You cannot predict the future of that one. So basically what is the idea here that, what I'm trying to say here is that if I want to predict the future of the system from the initial one, I need two things. One is the coordinates, and the other one is the velocity. Okay, so this is the important thing is like that. Okay, so basically I need two quantities to describe a system in a space, right? One is the coordinates, another one is the velocity. Now, if some space, describe the system in a space which needs the coordinates and the velocity, then that space we call as a phase space. Okay, so this is a very well known word. I think whatever be the topic of research you are going to do, you know, you would always heard this thing that's called the phase space. So for a system, you know, any space where you want to describe a system, you need at least two things. One is the coordinates and the velocity of that one. So that we call the phase space. Now let's generalize this system, right? So this velocity and the position. So instead of like this x, y, z, like in the Cartesian system that we are using, say let's use some generalized coordinate system. So what they mean by generalized coordinate system? So say this generalized coordinates. So in the generalized coordinates, what you can do, the coordinates we normally going to represent by this q1, q2, q3, say this n number of, so you have this qn, right? So we need another one quantity that is called the generalized velocity. Say this is q1 dot, this is q2 dot, and you can say like in number of particles, so we have this qn dot. So now we are representing this system by generalized coordinates in the phase space, which has this generalized coordinates represented by this q, and you know all these generalized velocities are represented by the q dot, right? So this is one. Now let's take an example. So normally if I say this Newton's motion, you know what we know, this m into x double dot or m into q double dot actually is nothing but the force. That is the Newton's law, right? Say we are considering a 1D motion. To understand, so let's understand this phase space in more details, okay? So yes, say like you have a particle, single particle, which has a mass m, and so the generalized q, which is nothing but the force, right? And now the force can be a function of these generalized coordinates, can be a function of generalized velocities, and we can be a function of time. So we will describe each of the term of the force term in very details, because this is a very important concept that we are going to use here. So you see this, the force in the right hand side, you know, this force, you know, this for a simple harmonic oscillator, you all know this force is nothing but this minus k times q, right? So basically what we found that, you know, this force is a linear quantity and is a function of the generalized coordinates, say q. Now can you tell me some example where the force is a function of generalized velocity or velocity? Can you give some example?
Frictional force.
Damping, frictional damping.
Great. And another some extra?
Lorentz force.
Particle is in a magnetic field.
Yes, yes, great. So, so you know, and then let's come to this thing. So in the frictional force, is it proportional to velocity, or how is relation looks like? Is it proportional to velocity or square? How?
It depends. I mean, if we are dealing with viscosity and then in a certain velocity range, it's proportional. But in if the velocity is really too high, it can be square proportional to velocity squared.
Okay, great. Okay, so now, so that's true. So let's you can say this if you consider even for this this Lorentz force, it's also B cross beta, right? So basically, what I'm trying to say here, this force can be just function of explicitly function of this position or the generalized coordinates. It can be explicit function of the velocity. Okay. Now try to come to this third thing, where we are saying this force can be explicit function of time also. So can you give me example of this one also? Can you give some example of this force which is explicit, explicitly depend on time? You all know this force very well.
Particle is in an electromagnetic field.
Great. Yeah. So basically, the thing I think what you are saying is correct. Is any force which has this explicit dependent sign e to the power I omega t minus some spatial dependence also. Okay. So what you have found here that it has an explicit function of this time. Now, so why I'm stressing this point here? It's very important. Is this? If you have this force is a function of q, then you have one kind of things. If you have a force is a function of q dot, then you get one kind of things. But if you get a force which is explicitly depend on time, then things are very complicated. Okay, so the reason I'm saying, so now at this stage you say we are saying this is explicitly depend on time. And if you some system in which this force is explicitly depend on time, that kind of system we call non-autonomous system. You will see that why it is so important. Like if it's a function of time, we will come to this point actually. In the phase space, you will see why it is so important. Okay, so basically what we see that we have defined the phase space, which basically needs these coordinates as well as the velocity, and we can generalize the system. And if I take any motion where the force can be a function of generalized coordinates, generalized velocity, as well as it can be a function of explicit function of time also. Okay, so now let's take this example of simple harmonic oscillator, because we all are familiar with these things. So now say this is m of q double dot is equal to minus k times q. Right? So this is the equation of motion, and you can write down this equation as simply like minus omega squared times q, where this is the this oscillation frequency and k by m square root of that, right? Now, what is the so important about this simple harmonic oscillator, or the force associated of the simple harmonic oscillator? It's that this force that we are saying, this m of q double dot, right? M of q double dot is equal to the force that we have on the right hand side. So this is basically actually is a conservative force, right? So if you have a conservative force, then you can always get this force from a potential, right? So that is the beauty of this simple harmonic oscillator force. So you can easily get this force from a potential. Now, in this case, we are considering the force is explicitly function of q only. Okay, because we are not considering a damping or anything at this stage. So this v actually you all know is nothing but this half omega square into q square. So that is the potential, and from that one you can easily get this one. Now come to this equation. So what is this equation? This equation has is a second order equation, right? So if I split into two first order equation, then what you will get, say this q dot is equal to v, if I define that way, and this v dot is equal to minus this potential, which is a function of q, derivative of that divided by m. Right? So it's the same equation that is written in the above. So we get basically two first order equation from this second order equation. Now the thing is that what I'm trying to say here, in the definition of this, when we're discussing about these particles, they are moving, and we say that in the phase space we need basically two things. One is the coordinates, right? And another one important things that we discuss is the velocity. So basically, if I want to solve these equations, so in addition to that, what I need this initial conditions. And what is the initial condition? Say that Q at 0 is equal to something and Q dot at 0 is equal to some value. Right? So I basically need two things. One is the initial condition of these generalized coordinates, generalized velocities, and these two equations that we have. Now, if you do these things together, this equation of motion in the 1D, sorry, in the first order and the initial condition, if you jointly do them together, what you will get? Okay, it's happening like that. Should come to this. Don't know. Okay. Okay, maybe. Sorry, I think some issue with the pen. What happened with the pen? Okay, so maybe I can try with another one page. So I will write it again. What happened to this page? I don't know. I don't know why it's happening. Sorry, there is some problem with this pen. Just give me 1 second. I don't know what's happened. We try to connect it again. Yeah, so now it's working. So basically, what I was trying that, so Q dot is equal to V, you have one equation, and another one you have this V dot is equal to minus V prime, which is a function of Q divided by this M. And with this initial condition that we have, so if we do this together, right, so we must get a unique solution. Right? So how you are solving this equation, it really doesn't matter what method you are using. But if you do this, solve this equation, and if you put the initial condition, you always get a unique solution. These two things together, right? So that is the main idea behind that one. So now actually we will use this idea of this unique solution to describe the phase space. Okay. So for the phase space, what we have, we basically say it's a phase space, right? Say, this is Q and this is Q dot. Now in the phase space, what we have discussed till now, that we need to know about the initial position and the velocity of the particle. Say this is the initial position and the velocity of the particle. So it has this initial, this Q of 0 and Q dot is 0. So I know this initial position and the initial velocity. And if I this initial condition, and if I solve this equation, I can get the next time step. How the particle will move in this phase space. Say like this particle is moving like this, all kind of according to the conditions, it is moving like that. Correct. Now, just imagine this this phase space is going like that, and you have a case like that where this phase space is cutting its own trajectory. So it's going like that. Okay. So what we did here, that in the phase space we know the initial position of the particle and we know the initial velocity of the particle, and in addition to that, if we know the equation of motion, so we can easily get the trajectory of the particle. So this is the trajectory of the particle in the phase space. And what I did, I just do one thing, like I draw the trajectory in such a way such that this trajectory, phase space trajectory cut itself at some point. Now the question, the most important question here is that, can this phase trajectory intersect themselves or each other. That's the important things to understand, right? Because you know the equation of motion, you put the boundary condition or the initial conditions in. And you can easily get the phase space trajectory. Now the important question here is that, because you know the force, right? This can be any force. Here we take the example of simple harmonic oscillator, and this can be any force because we decided that the force can be a function of generalized coordinates, generalized velocity, as well as the can be explicit function of time also. So the question here is that if that kind of force, this trajectory that you draw, the phase space trajectory, can they cut each other? I mean, intersect each other?
No, sir, they cannot intersect each other.
In case of oscillations, it may be possible.
Okay.
Sir, they cannot intersect each other, sir.
They cannot.
Okay. That's what you say. This one. Another one. You say something.
So in case of oscillations, maybe we may think about it. If oscillations happen.
Okay. Well, these two. Anything else? I mean,
Maybe in case of
okay.
conservative field, it won't intersect. But if the field is not conservative, then it may intersect.
Okay, so I think all of them are, in certain degree of freedom is correct. I mean, all the three answers that you have in certain degrees of, degree, they are correct actually. So let's try to understand, like why that, whatever the discussions that we have, you can easily understand this. This is a very simple logic, behind this phenomenon. So what we are trying to say we have this equation to see that we have some equation of motion and we put some initial condition, right? And it will give you a unique solution. Unique mean like whatever be the way you want to get solve this equation, it really doesn't matter. At the end of the day, you should get the right and the same thing, right? Now, the thing is that if just imagine you consider this is the starting point, right? Say this is the initial point we have, right? So it's going like this and it's coming like that, correct? Now say that this one also have some initial value, say like q, q prime 0. This is the generalized coordinates, and say like q prime dot, this is dot. It's also say like at say dot t is equal to say like t at t time, and this is also at t. You know this initial condition at this point. Now, the thing is that with this initial condition and the equation of motion that you have, you must get a unique solution, right? Now, the thing is that you see here, if you go like this way, you have two branches. One is going like that, another one is coming like that. Is it not? See, one branch is going like this, but another branch is like this. There are two possibilities, like two solutions it can have. But what is the condition? What is the things that we discuss is that if you put the initial condition and if you have the equation of motion, it should give you the unique solution, right? But here what we found that it has two branches. So that is not possible, right? So, but the thing is that, is it really not possible in any scenario? So it is not like that.
Sir,
So
if our force is non-autonomous, then probably it's possible.
Exactly. That is the idea behind this. See, if it's not the thing is that if you know the previous all those things, then you can basically predict the future, right? But the thing is that if the quantity, the force, which is itself is also changing with time. So these things, whatever things we are defining here, then we are basically violating that one. Because this just imagine if this is a function of time, right? This explicit function of time, then what will happen? You are basically changing the initial condition itself. So basically what happened, you are basically changing the main condition of this game. So as a result of that, what will happen? This trajectory can intersect only when this force is an explicit function of time, or otherwise it will never intersect. Okay, so because the thing is that if you do not, this force is not a explicit function of time, then you should get a unique solution. But here we are getting the two branches, right? So the only possibility is that we can get, because if you change the initial condition of the system also, and that you can do if you make this system is non-autonomous, or by making this force which is an explicit function of time. Okay, so in that scenario, so basically you can make it. So this is an actually important theorem which tells that if you make this force to be explicit function of time, or if your system is not autonomous, then only they can cross each other or cut each other, whatever you will say. Okay, so this is a one kind of this trajectory on the phase space that we had drawn, and you can say draw another one, say like this is q and this is q dot. So like I say I'm here, this particle initially is here, and it's going like something like that zigzag path in the phase space, and ultimately you are coming to the same point from where you have started. Right, so this should be q dot. Right, so basically you have a particle, and that particle has some initial condition, and moving under certain force. And it at every time you can draw the phase trajectory, and at the end of the day, if this phase trajectory is coming to the same point where you started, then we call this as actually a periodic motion. So like case of a simple harmonic oscillator, if you do a 1D, it is oscillate and coming back to the same position, right? It's oscillate like this. So basically in that case, if you can repeat the phase space, then you basically get this motion is we call this is a periodic motion. Right. So this is actually the idea behind the phase space and how this phase space can be drawn. Like you in your research career, you always you may need to draw this phase space trajectory several times. It's an important topic to understand. Okay, but and also when they can cross, when they cannot cross. Also this periodic motion, right? If you start from one point and if you know the initial condition of that one, they are moving. This particle is moving into that in that field, and what happened. After certain time, it can come to its initial position, and if these things happen, then we call this as a periodic motion. Periodic motion. So this is basically the phase space things that we need to understand one. And since we are discussing a lot about this simple harmonic oscillator, so let's go a little bit more about this simple harmonic oscillator also. So with that one, we will finish today's class actually. So consider simple harmonic oscillator. Okay, so and the equation of motion, that is actually is nothing but this q dot is equal to v, and we have this v dot is equal to minus omega square of q. Okay, so we are not considering any damping or anything like it. This is like undamped simple harmonic oscillator, right? So this is a time derivative, so we can write down this is as a dq of dt, which is nothing but this velocity, and this is actually dv of dt is equal to minus omega square times q. Now if you divide these two equations with each other, what you will get? You get this dv of d of q is equal to right, minus omega square into sorry, should be v should be here, right? Now if you do this one, so what you will get? V dv is equal to minus omega square q into dq. So if you do the integration of this equation, so what you will get? Half of v square plus half of sorry, should be omega square q square is equal to constant. Correct? Now, basically, so this constant actually constant of integration. Now, you see these things. We can play it with this equation. If you just multiply this equation with the mass of the particle, which is having this simple harmonic oscillation. So what you will do if you do this half m of v square and half of m omega square of q square, then what will be this constant of integration? This will be nothing but the energy of that simple harmonic oscillator, right? Say this is E. Correct. So we know the constant of integration. If I multiply with the mass of the particle, which was having this simple harmonic oscillation. Now what we found that this is basically nothing but this total energy of the system. Now, so this is V is actually nothing but if I say further simplify this, m into q dot square plus half of m of omega square of q square, that is equal to E. Now let's draw a phase space diagram of this one. Okay, so this is Q and this is Q dot. Correct? So now tell me what is this equation? How it looks like?
Sir, an ellipse.
Great. So, so first let's draw an ellipse. Okay, maybe drawing is not that good. Okay, yeah, but some kind of ellipse. Okay. Now, if you see in the last slide, what we discussed. We discussed that we have a particle starting from somewhere, right? And if you know the initial condition and if you know the equation of motion, so you can predict the future. What will be the next position, right? So if you in the phase space. Now the thing is that basically you know that the direction of the trajectory in the phase space. So in this case also we should know what will be the direction, this side or that side. We need to know what will be the direction of that one. Right? So now we know what is this position, right? So if you know this one is at this point, this velocity is 0, right? At this point, this velocity is 0. So if you make this is equal to 0, so you know what will be the expression for this q here. So this will be square root of 2e divided by m of omega square. Right. So you also can do the same things about this point also. So at this point, this q is 0. If I consider this as origin, actually, right? If you do not consider this as an origin, then you get some shift in this ellipse. So if I consider this as a origin here, so at this point, this q is equal to 0. So what you will get here, so basically you get this 2e divided by m. Right? So we know this each position, what is the value at this point. Now, so this ellipse that we draw, that is for a given energy, right? So this is the E. So for a fixed energy, I got this ellipse, right? Now, if you increase this energy, right? So you get this, this concentric ellipse, all this. For a different energy, you will get another ellipse like that one. And you can further, with different kind of energy, you will get all these concentric ellipse. Now, the thing is that how we should define the direction of that particle. Now, if you consider a simple harmonic oscillator, it is oscillating like this in one day, right? So just even from here, it reaches to this point. Now, when it reaches to this point, this q is maximum, right? Then it starts moving in the other direction. So as a result of that is here, this velocity goes to 0. Now, if I want to move, see if I consider this as a positive direction, if I need to move in the negative direction, right, then what should I have? I should get the direction of this direction. Is it clear to you all?
Yes, sir. Yes, sir.
Okay, so it's a very simple, like whatever the things you know, like, if you have a simple harmonic oscillator, it is moving around its mid position, like that we have. Now, when it reaches to the maximum point, it has to return, right? Now at the maximum point, this velocity goes to 0 and then it reverses. But when you reach to this point, it should go to the positive direction, like this point. So you see, we are going in the positive direction. So this will be the direction of the trajectory of the phase space. If we start with this is the particle, then you will go like this way. And similarly, you can get all this for different value of this energy. As I told you, this E, different E value. So all these things also you get concentrated this ellipse, and you can get easily this one. Now there is only one exception here. That is if you reach to the this origin. Now if you reach to the origin, this origin actually itself is a trajectory. Okay, but here this E is 0, right? So you always stay here. You will not go anywhere because the energy here is 0. So you will always stay here, and this is the actually is nothing but the equilibrium point. So the point that this is the equilibrium point. Actually, at that point, the energy goes to 0, and this point itself is actually its trajectory, and it will always stay here. But if you have a finite energy, this particle, the trajectory can go like this way. But if the energy is 0, which is at the equilibrium, right? So it will always stay there. It will never go to other point. Okay. So this is an important understanding of the simple harmonic oscillator. You can do this calculation for if you introduce this some damping on this one. You can do this calculation with that one also. So you get different kind of things over there. So that is the things we will finish today here. So basically we finish all this this coordinate system, generalized coordinates, and how we can define this constraint like this, especially the holonomic constraint, non-holonomic constraint, and what are the inequalities associated with the system. And especially if I want to describe the motion of a system or a particle in a phase space, right? We always need to know about two things. One is the initial position of the system as well as the initial velocity of the system. Without that, you cannot predict the future. I mean, you know the present situation, but if I ask you to calculate these things at the later stage, I mean, at the next time, you cannot calculate without knowing that one. And so, for defining the phase space, we need two quantities, as this is defined in the position as well as in the velocity in the generalized coordinates, right? And with that one, we found that actually force will play a very important role in defining the phase space trajectory. If there is a function of these generalized coordinates only, the life is simple. You can get a very easy trajectory like that one. But if you get this time-dependent force, explicit time-dependent force, then your trajectory may have cut. You get different kind of trajectories. They will cut each other or something like that. Okay. And another one important thing is that in the trajectory, space trajectory, if know the initial position of the particle and the initial velocity of the particle, they can move in the phase space. But if they come to the same point, maybe in a different path, but we can consider, we call this kind of motion is actually nothing but the periodic motion. And for a simple harmonic motion, you can easily demonstrate this very easily. Okay, so these are the things for today. And with the understanding of these generalized coordinates and the phase space that we have here, and especially these degrees of freedom, which is a very important quantity. So next year, what you will do, you will start this Lagrangian equation of motion. So how we can derive the Lagrangian, and for a different kind of system, like we need to derive that equation, and basically the equation of motion. So and you will see that this Lagrangian equation of motion that we are going to do is not only to just use to calculate the equation of motion for this Newtonian mechanics. Actually, it has this application beyond that. So this Lagrangian is very widely used and also very generalized can be used in different kind of system where this Newtonian equation of motion cannot be used to every system. Okay, so that part you will discuss in the next class. So do you have any question regarding today's class? Or any suggestion you have? Like the speed of teaching, so I should teach little bit slow or something like that. You can tell me. See, if you do not tell me, I do not understand. Like, what is the problem you guys are facing, right? So let me know, then we can do accordingly.
Hello, sir.
Yes, go ahead.
Yeah, sir. I had just one. Wait a minute. There is echo. Sorry, wait a minute.
So you will do it a little bit slow. You want to say?
No, sir. So I basically want to ask that. Let's say if our phase space is of n dimensions, or n dimensions. So and the trajectory is basically like a curve, right? So do we have to? So like one way that you said is to basically solve these two equations, these two coupled equations that we can first order to find the curve, or if we can find, say, n-1 constraints, n-1 as n-1 equations that relate these coordinates, then is that also like, is it the same as saying solving these equations, or is it different on its own? Like if I can find n-1 constants of motion, or things that relate q dot and q, n-1 of these, is that a different technique of finding the phase space trajectory, or is it the same thing in different words?
See, I think so. If you do not know, just imagine the case. If you do not know like Lagrangian and Hamiltonian, then you need to solve the standard equation to get equation of motion for a given system, right? But if you know the Lagrangian of a system, it's much more easier to solve the equation, get the equation of motion, correct? So like there are different methods you can adopt to solve the same equation. Now the point is that, so that is the things that I'm trying to emphasize here, is this one, that if you adopt different method, but if you use the condition that is given in the system, at the end of the day, you should get a unique solution, right? That is the main point. So if when we go to this Lagrangian one in the later one, you see the life will be much more simple to get the equation of motion for all these things. So that is actually one way of solving the equation. But it really doesn't matter which method are you using. You should get the unique solution at the end of the day.
Yes, sir. Okay.
Okay. So actually these are different methods. It's like when this Lagrangian methods was not available before this Lagrange, Lagrange, derived all these calculations. So people do not know how to write down this Lagrangian of a system, and from that one you can easily get the equation of motion, right? So they use normal standard method to get all those things, right? But when you know the Lagrangian or the Hamiltonian, your life is much more simple, because that gives you one extra freedom to do the calculation. Okay. Okay, then so.
Sir, can you please explain me the part where the degrees of freedom went negative?
Degrees of freedom. So basically the things that I was trying to explain this here. See, this system you have, this normally if I tell you, okay, you have a one particle somewhere, which is like, you can consider this a stationary particle, right? Now, what you need to describe that particle? Basically the position, right? Now the thing is that if you have a system of two particles, say then you need 6 coordinates. Now the thing is that if you have a large number of particles present in the system, now the question is that what is the exact number of degrees of freedom to hold the system or to describe the system, right? So now the thing is that you can do different way of doing the calculations, but if you can find the optimal value in some way such that you can describe the system, then your number of equations will be less, right? So if you increase more number of degrees of freedom, you need to solve more equations and you need more conditions, because you see we need two initial conditions for each equation, like the position and velocity, right? So if you have more and more equations, then you need more conditions to solve. So if you can optimize the system by a certain number of degrees of freedom such that you can describe the system with that, then it will be easier for you.
Okay, sir.
Okay. So is it okay? Or then how to stop recording? Okay, here. So I'm stopping now recording, okay?